Okay, let's begin. Are there any questions on 11.1? Did I assign?
Yes.
Huh? 43? What does that say? What does 43 say?
It was like matching graphs with their traces. You were given a function and you had to match it to the graph of it.
Oh, so
And-
it would depend on. I think you just have to do those level curve things then, right?
What about z equals sine x minus
Z equals sine x minus y,
y? Yep, right.
like that.
Hmm.
Okay, and what were the other options?
That was,
It was just like find the graph.
there was like pictures of the graphs.
Match it with
Well, I don't know what the pictures were. Okay, match the function with this and that,
That is going to equal z equals 0.
with a through f and with its contour map. Okay, so what do we know about sine x minus y? Tell me some properties of that function.
It's going to equal 0 along the line x equals y. Z equals 0. Along the line x equals y.
Along the line x equals y, it's going to equal to 0.
Yeah.
Yes? What else do we know? What's its maximum value?
1 and negative 1.
And its minimum value is -1, right?
Yeah.
So what? So obviously that eliminates some of these functions, like a and b are out of the question already. D would be out of the question. It's a sine graph, so you expect it to be bouncing up and down all the time. So you expect it to be either this guy, or that guy. How do we choose which one?
Draw the line x equals y.
Okay. So the line x equals y would be coming out of the xy plane. So I know here, this is the line x equals y, z is 0 on this line. So it's going to be one of these graphs bouncy up and down, but when x equals y, we always hit 0. So which graph has that property?
Corner, bottom corner.
This one. Right? Notice that along x equals y, it's hit 0, and it's actually bouncing up and down as you would expect a sine. So that's basically it. You're just looking at the properties of the function and trying to match it with the graph. And once you have this guy, what do you think the contour map would look like? So you're just slicing it now to find level curves, which one it would be. All right? Well, the guys with the circles, they would have to have like the top of hills, right? Those guys are actually high elevations, right? It's going to be this one. So that's basically it. And C, that would be the sine of x times y, because that would be where x or y is 0, which means along the x-axis and the y-axis you'll hit 0, and so on and so forth. So that's all you're doing. You're just looking at the function and trying to see, well, how would this behave? My z value would never pass my plus or minus 1. That would be the bounds. It'll be bouncing up and down like sine, and it's 0 when on the line y equals x. Right? And it's 0 on any line where x minus y is a multiple of pi, and you get these guys. Right? So if you look at x minus y equals n pi, right? So then you have like y equals x minus n pi, right? So those are just straight lines, right? They all have slope 1, so you expect the lines to be parallel, right? So they're all going to be lines that look like this, right? And your function will be 0 on all those lines. Again, that's the only function that matches that description. So that's basically the idea. You're just looking at the functions, how they behave. Other questions? What does it say?
With a contour map or a function f is shown, use it to estimate the value of, I don't have to get this.
So yeah, for this one, it was graph A was the answer and contour map 1.
Oh, that's what it said?
And this, and now we're looking at 21. Contour map of f is shown, use it to estimate blah blah blah. So this is the contour map here.
Very steep, but I didn't get that one.
So it's just a circle. So it's called, this one is 70, this one is 60, this one is 50, and there's a 40. And one is here, it's on a grid, it's very hard to see. So basically we want to estimate f of minus 3, comma 3, and f, so we're estimating approximately equal to, and f of 3, comma minus 2. Basically just find these points on the graph, right? So if we look at minus 3, comma 3, so we go 1, 2, 3. On this grid it seems to end up between 1, 2, 3. It's just beyond the 60. So 3 seems to be here on that graph, and as well as 1, 2, 3. It's between the 70 and 60. So this is 3 here. So your point ends up somewhere in this region. So it's going to be somewhere between 60, this is the 60 line, and that's the 50 line. Right? So I guess 55, something like that. That's it. So you're just looking at the heights. Remember the height, these numbers on the curves give you the height of the function. Right? That gives you the z value. So you roughly identify a point on this grid and just sort of estimate based on the value of the lines that you're in between, like what value you hit. And this is just an estimate. It's like a picture. You can't really tell exactly what's going on. And you do 3, which looks like 1, 2, 3. That would be between here was the 3. And minus 2, which looks like 1, 2. Between a 30 and a 20. Minus 2 was down here. There's like a 30 and a 20. So it looks like it ends up somewhere here. So I would guess that's some value around 25 or something similar.
I think it's actually a little higher on the graph. Yeah, it's like 35.
Oh, so it'll be at like here. Yeah, so that's it. It's just showing you how to read contour maps. It's not an important idea to remember. Like you never get tested on graphs like these. It's just to help your intuition a little bit. Other questions? Okay. And pass up the homework. By the way, due to the religious holidays last week, I'm accepting late homework this once. So anything from 10.6 up to 11.1 I'll take today, if you have it. Make sure I have that by the end of the day. So if you don't give it to me now, make sure you see me in the tutoring center and give it to me before 5 p.m. pass here one more thing. Yes.
I have a question on the test. Is it going to be full period or half?
The test, it's an hour and 15 minutes, I think.
And will we then do class after that?
We'll probably do a little something after that. Because today's topic, I don't think I'll finish it, but the last part I might do right after the test. It shouldn't take long.
Okay.
Define need extra time. Nope, the only people who can get extra time are those who have documentation to say that they should get extra time, in which case we'll have to make arrangements with the center downstairs. Everyone else, hour and 15. Moving on to 11.2. We're going to talk about limits and continuity. Hopefully you guys remember about limits from before. So we're going to skip the epsilon-delta definition of limits. So if you see that in your textbook, you can ignore it. In practice, it's difficult to, it can become quite difficult to actually use it, so we don't really do it. And it's almost pointless to actually cover it in Calc 3 anyway. The only people who would use the epsilon-delta definition to compute limits are mathematicians. And so an engineer, you'll never use it, right? Physicists will never use it. No one's going to use it except a mathematician. And if you are going to be a mathematician, you're a math major, you will use that in advanced calculus. You're going to spend a lot of time computing limits by epsilon-delta. So for our purposes, we're going to strictly ignore it. We're going to do a more intuitive approach, and instead of using the epsilon-delta definition to prove limits exist, we're going to use something called the squeeze theorem for limits, and I'll show you how that works soon. Let's remind ourselves in single variable calculus how limits work. The ideas are the same, but we're going to bump up the dimensions a little bit, and we're going to see how things change. So if I write this expression, what does it mean? In layman's terms, general terms, don't even have to be too mathematical. Just sort of. No?
The limit of f of x as x approaches a is equal to L.
Yeah. Explain what that means.
It means that the function f of x, as it approaches the x value of a, it has a y value of L.
Right. So this means the y value gets close to L as x gets close to a. Right? That's what it means, right? A limit is basically a y value. So you're manipulating the x value some way, and you're looking at what happens to the y values. And as long as you approach a certain y value, you say that's the limit. So, for example, plugging in the point is not the right way to think of it, because that only works if your function is continuous, right? It's possible for your function to not be defined at the point, which is why the word close is actually a pretty important distinction here. You're talking about proximity. You're getting close to A, right? And the y value is getting close to L. You don't actually care about being there. So for example, you can have here, where this point is undefined, but I'm approaching this guy. Let's say this is the value 2, right? And the y value here is 3, right? I can never actually get to the point 2 or attain the value 3 because there's a hole in my graph. It's undefined for some reason, right? But here I can say the limit as x approaches 2 of whatever this function is 3, right? I'm saying when my x value gets close to 2, the y values will get close to 3, right? And I can have various ways that this can happen, right? I could also have a function that is defined at 2 and 3, right? It's just a point here. And again, the limit as x approaches 2 of f of x equals 3, right? So we know the limit exists. Basically, the limit is the y value that you're approaching when your x value gets close to something. What makes the limit not exist? How do you know if a limit does not exist? If both sides don't have the same limit. There's something called the one-sided limits, remember? You looked at the limit as x approaches a from the left, right? This is approaches a from the left. Right? Of f of x. Now, if that turns out to not be the same as the limit as x approaches a from the right of f of x, approaches a from the right, then the limit as x approaches a of f of x does not exist. Right? So what would happen in that example? So something like this can happen. You can have what you call a jump. Right? So let's say, again, here I'm approaching 2. The y value here is 3. The y value here, though, is 4. Right? So now as I'm getting close to 2 from the left side, right? Meaning I only care about what's going on the left side of 2, which means I care about this curve. I'm moving along this curve, my x values are getting closer to 2. My y values are getting closer to 3, right? However, if I only focus on what's going on the right side, then I'm on this curve, and I'm traveling towards where my x values are getting closer to 2, my y value is now getting closer to 4, right? So if I ask, what is the y value that we approach when x approaches 2, there is no answer. Because you're like, it's 3, wait, no, it's 4, wait, no, it's 3, no, it's 4. Right? There is no answer. There is no y value that you approach, right? So we're approaching the x value 2, but there is no single y value that we're approaching. So because the left and the right side don't agree. Whenever this happens, we say the limit does not exist, right? It doesn't matter if you're continuous at the point, the limit can exist whether or not you're continuous. That's not the issue. The issue is, do the y values match up when you're approaching from different directions, right? If they don't match up, we say the limit does not exist.
That function would be technically considered not continuous, right?
No, that's not continuous. We're going to talk about continuity later. I'm not sure if I'm going to get to it today, but we'll talk about it. So this is the only function that's continuous because two things have to happen, and we'll talk about that later. Okay, so I just want to remember what a limit is, knowing that it's the output value that you approach when your input value is approaching something, and knowing when it does not exist. If I can find two directions where my y values don't match up, it does not exist. So let's up the dimension a little bit. It's possible to define a limit that looks like this, which I wrote something on your quiz that asks you to talk about what a limit means. Okay? So let's say I have this expression, right? So it's very similar to the one before, except now I'm not just worrying about x, I'm worrying about the pair xy approaching some coordinate, right? Okay, so in layman's terms, tell me what you think this means.
The limit is z is equal to L on approaching and xy is equal to z.
The z value gets close to L as x comma y gets close to the point AB. That's what it means, right? So again, we're looking at the output values, but now we have two input values to worry about. So now we have that. Now let's talk about what has to happen for this limit to so what makes that not exist? What do you think? What can go wrong for this guy to not exist? What can break?
Either the X or the Y.
Well, what can happen before, right? If our directions, if we're approaching from two different directions and things didn't match up, that's when our limit doesn't exist, right? The output doesn't match up when we're approaching different directions.
So it's a very long continuity bridge, right? The values is
No,
not-
limits have nothing to do with continuity. Limit can exist even if it's not continuous, right? That's the case where you have a hole. That's very possible. So here's where the thing breaks down. Very similar concept to the single variable case. However, notice that when you're looking in here in the single variable case, right? You're approaching an x value, right? How many ways can you approach this x value? Two. You come from the left, you come from the right. Now you have a point in 2D space, A comma B. How many ways can you approach that point? Four? It's an infinite number of ways. Sure, I can come in from the left, I can go from the right, from the top down, from the bottom up. I can go in as a diagonal. I can twirl you around over here, boom. Coming way from right field, boom. Come all the way over here and come back, boom. Right? I can go in along some kind of parabola. I can go in along some kind of cubic. I can go in as an exponential. Infinite number of points. Right? So when does this limit not exist? Same time the other one didn't exist. If two directions do not agree, if I don't get the same z value by approaching any two paths, then the limit won't exist. Because then I can't say the z value approaches this number, right? Because I know, oh, if I come in here, I get this z value, but if I went along this path, I get a different z value. It means the limit can't exist. There is no z value that you approach when you approach that point. And of course, this concept extends. I could do a 3-variable limit, x, y, z approaching some point, and then whatever output I call that, like w, right, or something like that. The same idea will apply, right? So that's basically the idea. And in this case, we can show a limit does not exist. Very similar to how we can a single variable limit does not exist. So the idea is, all I have to do is find two directions that don't match up. Now, obviously, there are going to be some challenges, right? In the single variable case, there are only two directions to check. But if I know I can approach a point from infinite number of directions, how do I find the two paths that I'm going to pick to show that something doesn't exist, right? That's the idea. And worse than that, if I want to show that a limit does exist, how am I going to check an infinite number of paths to show that all of them will give you the same z value? That we'll do later. Right now, showing it does not exist is easier, so we'll do that first. Let's actually illustrate with an example, and then I'll actually give you guys some steps. These are very important problems, by the way. You always have a problem like this on your final, to like find a limit or show it does not exist. So pay attention now. Show that the limits do not exist. Meaning, find two paths where the z values don't match up, right? Here are the examples. Limit as xy approaches the origin of the function x times y over x squared plus y squared. The limit. They'll usually ask you about things approaching the origin because it's easier to write down functions for that case. X squared plus y to the fourth. C. See, I changed it up just a little bit. Just going to 1, 0 over x plus y minus 1. D. Limit as xy approaches 0, 0 of the function x squared plus sine squared y over 2x squared plus y squared. We're going to show that these do not exist. And I know what you're thinking. Of course they don't exist. The denominator goes to 0 if we plug in the origin. Again, continuity is irrelevant with a limit, right? Let me emphasize that here. Continuity is irrelevant. Continuity is irrelevant. Right? And we knew this even with single variable limits, right? For example, this limit. Limit as x approaches 2 as x squared minus 4 over x minus 2. We actually can't plug in 2, right? The function doesn't exist at 2. It's not continuous at 2. However, we can still find the limit. Remember how we found that limit?
Break it up into x minus 2 times x plus 2.
Right.
Over x minus 2. And you cancel out x minus 2.
Right. You can cancel a bad point. And so this limit ends up being 4, right? So it's like you had a straight line. It looks like x plus 2, but there's a hole when you get to the 2 value, which gives you a y value of 4, right? So continuity doesn't matter. It doesn't matter that the denominator goes to 0, because remember, we're not actually plugging in that value. We're just getting close to that value. We never actually divide by 0. So don't let that fool you. It's possible for a limit to exist even though the denominator is approaching 0. So be aware of that. But these do not exist. How would I show it? So let's do the first example. I need to find two paths that give me a different z value. Give me a path. Okay, so let's say we're going along the path y equals x. Notice that this is a line that goes through the origin, right? Now along y equals x, what does my limit become? Let's say I call this L. Along y equals X, L would be the limit of y. Replace all y's with x's. I'll get x squared over, if this is an x, I get 2x squared at the bottom, right? These cancel. So the limit's a half, right? Tell me another path.
Y equals x squared.
Y equals x squared. Okay? What would happen? In this case, the L would be the limit of, if I plug in y equals x squared, here I get x cubed. If I plug in y equals x squared, here I would get x squared plus x to the fourth. What is that?
Determinants, you have to take the derivative of the top and denominator.
Do I have to do that? I mean, I could do that, but I could also just like
Pull up x squared.
factor out an x squared. Right? This would cancel into that. So I get x over 1 plus x squared. Now I can plug in x equals 0, and what happens? You get 0. So from two different directions, the limit gives me two different values. You guys are thinking too hard. I would have tried, how about x equals 0? Or y equals 0? Right? It's clear the top will just give you 0. Right? So if I approach x equals 0, y equals 0. So for example, if I approach x equals 0, my limit would just be plugging 0 for x. 0 divided by y squared. So that limit would be 0. Was an easier curve to think about, I think. Or y equals 0, my limit would be limit of 0 over x squared, right? Which again would be 0, which is different from a half, right?
So if you find, if you just do x or y equals 0 and then do one other,
Yeah, that would have worked, right? By the way, this means limit does not exist. Okay, so the people who told me about these paths, did you just randomly pick a path, or did you have, was there a method to the madness? Because I mean,
as long
there are
as,
an infinite number of paths. Why did you pick y equals x? There are an infinite number of paths that go through the point 0, 0. Why did you pick y equals x? Why did you choose that? As opposed to any other of the infinite number of choices you could have picked.
because it's easy to remember.
It combines the denominator. Okay, so there's no real guesswork here. If you know how to choose, you won't be stuck, right? There are actually ways that you can choose something. So let's look at the ways. There are things that you look for. One, choose an obvious path. What do I mean by obvious path? Like x equals a constant, or y equals a constant that passes through AB. Right? So for example, like I said here, I would have picked x equals 0, right? Or y equals 0, one or the other, right? So I choose like x equals 0, that's x equals a constant, and I can choose that constant because it will go through the path 0, 0. If I picked, for example, x equals 1, that would be a stupid path, because if my x value is always 1, I'll never go through the origin, right? So I'll just pick a constant that goes through the point. That's an obvious path. Just pick one and see what happens, right? See, your first step would be to choose an obvious path. To me, in this case, an obvious path would be one of these two. Yes.
So wouldn't the other be 0, so you'll be dividing by 0?
No, x is 0, my y is varying. My y I'm let moving. Right? So I'm approaching the origin along x equals 0, right? So x equals 0 is the x-axis. X equals 0 would be the y-axis, right? So it's like I'm approaching the origin here, or from here. So my y value is not 0, my y value is changing. The values are moving, right? So it's not 0. And remember, we never actually get to 0 because it's a limit. We're just getting close to 0. So I decided that I'm going to get close to 0 along the y-axis. Or I can decide I'm going to get close to the origin moving along the x-axis. My x is not 0 at this point. My x is just a variable, so I leave it as x. But if the top is 0, then the whole thing is 0. So the first thing is to choose an obvious path. Usually it'll be a constant that goes through one of the points. Usually I'll ask you the origin, so usually x equals 0, y equals 0 is going to be the obvious path. Right? This is just Calc 3, right? This is the easy life. Okay, so obvious path is the first thing. 2, it's not really a step, it's sort of a warning. Don't be redundant. It wastes time. Right? For example, notice that x equals 0 and y equals 0 actually give me the same answer. So if I test one, don't waste time testing the other. You can obviously look at this and tell if your x is 0, you're going to get 0. Or if your y is 0, you're going to get 0. So you test one of them, obviously the other one's going to give you the same answer. Don't do it again, right? So I'll see people like test a bunch of things, they get 0 a bunch of times, and then they do one where they get a half. You're wasting all the time getting all those zeros. You only need to show that 2 don't work, right? So once you choose something that's 0 and you get an answer, don't choose a path where you can just look at it and tell you're going to get the same answer, right? So, example, above, if you chose x equals 0 as a path, y equals 0 would be redundant. It obviously gives you the same answer.
So then that's why you say x or x.
Yeah, that's why I said or. Like I would never try both. That would just be silly. They both give me the same answer. It's obvious that they would both give me the same answer because they have a product in the numerator.
So then like if we chose x equals 0, then like if we did.
If I chose x equals 0, I would have gotten this, and then I would choose something else.
Okay.
Right? Now let's talk about the something else. What's the other thing that you would choose? I'll rewrite the examples now. Just want to have all these steps in the vicinity of the board. 3. Right? So we have one path, the obvious path. What's the second path that we're going to want to choose? Well, as John pointed out, choose a path that allows you to simplify. Example, which is a very common case, combine terms in the denominator. So if we go back here, you'd realize that in the denominator, I have x squared plus y squared. The denominator is actually the part that makes this thing complicated, right? Because if I plug in both zeros here, that messes up. So the denominator I don't really like. I'd like to choose a path that allows me to combine these two, right? So if you have x squared and y squared, making x equals y is actually a really smart choice. Because then I'd have x squared plus x squared, or y squared plus y squared. I can combine the two, right? Once I can combine in two terms, that means I can start canceling stuff, right? That will very often be the case. And that will usually give me another answer, right? So the first choice we'd make was we'd choose the obvious path. Second, be sure not to be redundant. Third, choose a path that allows you to simplify stuff. That's it. And so based on the function, you choose different things. It really depends on what you see there. But there's no real, oh no, I have an infinite number of choices. No, there are really only a few smart choices to make, right? And that's basically it. So
basically, for these examples, we'd just be choosing a function of y equals x.
yeah, y equals f of x, something similar.
Will we be doing this with 3 variables?
Yeah, you can do it with 3 variables as well. Maybe I'll do some examples of those. one thing to make sure, no one mentioned this, but I have heard it mentioned before. Be sure that the path you choose goes through the point of interest. Right? Other paths are illegal because they don't really make any sense. Consider them illegal. Right? So for example, with this function here, the path y equals x plus 1 is never a path I would choose because that curve does not go through the origin. It's a straight line. The y-intercept is 1. Right? So make sure whatever you're choosing, it actually goes through the points subject to these constraints. One is going to be an obvious path. The other one is going to be a path that allows you to simplify things. Right? And if a limit does not exist, those two choices will usually uncover the fact that it does not exist. So let's do the other example. Limit as xy approaches 0, 0, xy squared over x squared plus y to the fourth. This does not exist. Show me that it does not exist. Give me a path.
X equals 0.
Along x equals 0. I have my limit is equal to the limit of 0 over y to the fourth, which is 0. Give me another path.
Y is equal to x squared. No, x equal to y squared.
X equals y squared. Why did you pick that path? Out of the infinite number of paths you could pick.
It allows you to combine the denominators.
Can combine the denominators. Here I have an x squared, there I have a y to the fourth. If I double my power on the x, it gives me the same power as the y. Let y equals y squared. Then my limit would be the limit as plug in x equals y squared. So the top would give me y to the fourth. If I plug in x equals y squared squared is y to the fourth, added to the y to the fourth. Gives me 2 y's to the fourth. My y to the fourth will cancel. Gives me a half. Limit does not exist. Wow. Infinite number of paths. It hits them on the first try. Right? It's just following the method. Right? Choose an obvious one. Choose the one that allows you to simplify. There won't be that many to choose from. Let's look at part C. xy approaches the point 1, comma 0. Give me a path.
X equals 1.
Let's go along x equals 1. Then my limit would be equal to the limit of y over, if I plug in x equals 1, this is 1 plus y minus 1. Right? The 1's cancel, and the y's would cancel. And so that actually gives me 1. Give me another path.
Y equals 0.
Y equals 0. Then the limit is clearly 0. Right? Limit does not exist. In that case, both paths were the obvious one. To simplifying this, I could just use one of these variables to kill that other constant. So
You're only wasting your time if they both go through the same point.
if they both give you the same value,
Oh,
right? You want to prove it does not exist, so you want to show that the values are not the same. For example, limit x, y approaches 0, 0, x squared plus sine squared y over 2x squared plus y squared. Give me a path. Let's go along y equals 0. What would happen? My limit would be the limit of x squared over 2x squared, right? Because sine of 0 is 0, y squared is 0. This cancels, I get a half. Give me another path. X equals 0 seems like another nice path, right? What would my limit be in this case? It'd be sine squared y over y squared, which remember that sine y over y as y goes to 0 is 1. That's a special trig limit. So limit does not exist. You could have also chosen x equals y, and you would eventually be able to get to a different answer as well.
For part 2, wouldn't you get 0 over 0 for y equals 0? Is that okay?
No, if y equals 0, I would actually get the limit of 0 over x minus 1.
Oh, but it's okay if x approaches 1.
Yeah. X is never 1. It's getting close to 1. It's approaching 1. That's the important part. Yeah. So you sort of get the idea? So yeah, technically infinite number of paths, but you should be able to hit the two right away that give you what you want. Now, how do we show a limit does exist? So, back in single variable calculus, you just check the two sides. Check from the left, get an answer, check from the right, get an answer. Oh, they're the same, we're good. This actually doesn't work now in 3D, or even higher dimensions, because there are an infinite number of paths to check. Okay, I can check coming from the left, okay, check coming from the right, get the same answer. It doesn't count. Did you check coming from the, okay, just check that, same answer, doesn't count. Okay, come from this diagonal. Same answer, that diagonal, same answer, that diagonal, same answer, that diagonal, same answer, that curve, this twirling curve, right? Every time you check something, there'll be another thing to check, right? And you have to make sure that all of them work out. So how do we actually get around this? Well, you can use the epsilon-delta definition, which I said we're going to skip, or the idea is to use the squeeze thing. It's not actually the squeeze term. The squeeze term is used in the theorem, right? So there's a theorem that says the following, right? This is how we're going to prove a limit exists. It's the easier way. Suppose we can find a function g of xy such that f of xy minus L is less than or equal to g of xy, and at the same time the limit as xy approaches AB of g of xy is 0, right? So given some function, suppose I can find another function, which I'm going to call g, such that this relationship is true. And at the same time, if I take the limit, it goes to 0. Then the limit as xy approaches AB of f of xy will actually be equal to this value L. And that's as good as proving it works for an infinite number of directions. Why? Why does this work? How can we check an infinite number of directions like a boss with that? Because we're orthogonal. Oh, close enough. Okay, no, really, why? Suppose f minus L is less than or equal to G. What does this relationship mean? Simplify it for me. This is absolute values. If you have the absolute value of something less than something, what can you do? Right, you can put a minus G over here, f minus L less than a positive G over there. Right? Now, let's take the limit of both, all sides. Right. I'm not writing it out, but this is the limit as xy approaches a, b, blah, blah, blah. This is f of xy. L is just a constant. This is g of xy. Right? Now, what's your left side? Zero, right? My function g has the property that when I take the limit as xy approaches a, b, the answer is 0. Right? So this is f minus L less than or equal to 0. Right? So by the squeeze theorem, what does the squeeze theorem tell us in this situation?
The limit of minus L is equal to 0.
Right.
That's what I guess.
The limit of f minus L is actually equal to 0. If I'm less than or equal to 0 and greater than or equal to 0 at the same time, I must be equal to 0. That's what the squeeze theorem tells me. If I'm squeezed between 0 and 0, I must be 0.
That seems like the same sandwich theorem, but the same thing.
It's the same thing. The squeeze theorem is sandwich. It's the alternative name for the sandwich theorem. Right? Limits we know distribute across sums, right? So this is just the limit of f minus the limit of L equals 0. In other words, the limit of f equals the limit of L. But L is a constant. What's the limit of L? As you approach any point. It's just L. Right? That means the limit of f is actually equal to L, which is exactly what we wanted. Right? So if I can find a function, if, right? Big if, right? Such that when I put it in this in absolute values, it's less than that function, and the limit of that function goes to 0, I automatically prove that f, the limit of f is L. Right? So all I have to do is find this function. That's it. Find a function that does this, we prove the limit. An infinite number of functions. Oh God, how are we going to choose? Of course, there are tricks we're orthogonal. Okay. Let's look at how to find the function. Example. I'll use phrasing that they'll often use in a final. They'll say something like, find the limit or show it does not exist. And then they're going to give you a limit. So they might say something like the limit x squared y over x squared plus y squared. Of course, as you approach the origin. Right? It looks very similar to an example we did before. However, the limit actually exists in this case. So you're told this will be the question as it's phrased, a very typical way to ask the question, and they'll give you 2 or 3 limits under the question. So let's say, find the limit or show it does not exist, right? Which means they're not telling you if the limit exists or not. You have to figure it out, right? So if you're given this question, what's the first thing you're going to try to do? The easy way, right? Try to show it doesn't exist. Try to show it does not exist. Right? This is on the word try. I don't know if it exists or not, but I'm going to take a shot at it because I know how to choose 2 paths very efficiently. I can get through this very quickly, and it's just something that will save me time if it does not exist. I'm not going to just try to show it exists. No, I'm going to first try to disprove it. First try to show it does not exist. Okay? So what would be my paths here? Let's go along x equals 0. Then my limit will be 0, right? Because I'll have 0 over y squared. Tell me another path. Y equals x, right? Of course, y equals 0 is redundant. That would just give me 0. So let's try something that helps me simplify. Y equals x seems to help me simplify. Along y equals x, now my L becomes, let's replace all y's with x's. I get the limit of x cubed over 2x squared, right? And what's that? That's also 0. So now you're like, my boss method didn't work. So now you're trying to think, maybe the limit actually is 0. Could be. Let's actually check it. How do we have to prove it? Find a function g that does this. And if it does it, when I plug in L equals 0, then the limit is actually 0. So at this point, you're super confident in your abilities to pick the appropriate path. So when it doesn't work out, that jars you. You're like, oh, something's up here. Right? So that's when you go to the second. Try to find a function g. So what are we going to want to do? We think L equals 0. This means if I take f of xy minus L, this is just the same as f of xy, right? Because it's f of minus 0. F of xy is actually the function x squared y over x squared plus y squared. Now, can you tell me a function that is greater than or equal to that and goes to 0 at the same time? This is less than or equal to x squared y over x squared. What was your thought process in doing that? Right. So very usually this guy will be a fraction, right? We can make a fraction larger. There are two main ways, right? By making the denominator smaller or the numerator larger. Okay. So here I have a fraction. I want to find something bigger. My obvious choice will actually be increase the numerator or decrease the denominator. Y squared is greater than or equal to 0, so subtracting y squared from the denominator makes it smaller in theory. Therefore, in doing that, this guy will actually be greater than or equal to that guy. Well, what's this guy? Well, the x squareds cancel. Right? So this guy is just equal to the absolute value of y. And as x and y approach 0, what does the function y do? This actually approaches 0 as xy approaches 0. So, choose g of xy to equal y. Then, the limit as xy approaches 0, 0 of x squared y over x squared plus y squared is actually 0. And it's proven by the squeeze theorem. So that's the idea. Whatever you think is the limit after you try your boss method and you pick the two paths and the numbers seem to still give you the same thing, then you're like, maybe the limit is 0. So you go over here, you plug in what you think the limit is. Doesn't have to be 0, it could have been a 1, right? Could be 1 or 2 or pi or whatever, but you're going to just combine the fractions here, simplify, and you'll get to this point here, right? Now you're going to try to get something bigger, So you can do that by making the denominator smaller or the numerator bigger, and then hopefully you end up with a function that approaches 0. And once that approaches 0, whatever you put in here as an L would be your answer. So if I put in 1 here to make this work, 1 would be the answer here, right? It's not always 0. I just want to point that out. So that's basically it. There are still stupid mistakes you can make here, so let me just point some of those out. Something silly. I have this, x squared y over x squared plus y squared. Notice that this is also less than or equal to. I could have subtracted x squared from the denominator, right? I'd still get something bigger, right? I could have said this is that, right? Now why would getting rid of x squared be silly when getting rid of y squared was actually a smart move?
Because now you have the function x squared over y.
Now you have x squared over y, and as you approach 0, 0, undefined. I can't get an answer. I am stuck. It's a dead end, right? So not only do we want to make this thing smaller, bigger, but we want to do it in a smart way, something that actually gives me an answer I can work with. So getting rid of the y squared was the smart choice because I could cancel the x squares, right? Getting rid of the x squared would not be such a smart choice because then I end up with a potential 0 to the denominator, right? So there are still some things that you have to look for. Just make sure that your answer actually works out to something nice in the end. Let's try another one. X squared sine y over 2x squared plus x squared. So find the limit or show it does not exist. What are we going to do? Okay, how do we do that? What? Okay, so let's go along y equals 0. Then the limit is actually 0, right? Because sine of 0 is 0. Okay?
Y equals 1.
Y equals 1 is a bad path. Y equals 1 does not go to the origin.
Y equals x.
You could choose y equals x. What would that give you? That would give you the limit of, say, 2x squared sine x
Over 3x squared.
over 3x squared. The x's would cancel. This still goes to 0. Maybe it would be 0. How do we check? Let's see if we can find the function g. So now I look at f of x, y minus L, what I think the limit is. This is just going to be 2x squared sine y over 2x squared plus y squared. Make that bigger.
Get rid of the y squared in the denominator.
Get rid of the y squared. The 2x squares cancel. I just end up with sine y, which approaches 0 as xy approaches 0. This means choose g of xy equals sine y, and that proves that the limit as xy approaches the origin of 2x squared sine y over 2x squared plus y squared is actually equal to 0. see if you see this right away. I think I put something similar to this on the quiz. Not exactly this, but it's something similar. Does that limit exist? Well, you think that, right? If I let x equals 0, I get y squared, which goes to 0. If I let y equals 0, I get x squared, which goes to 0. If I let x equals y, the top becomes x to the 4th minus x to the 4th. I still get 0. I seem to be getting 0 from every direction. Can I prove it's 0? Let's say. You could try. There's something easier than finding g. Think single variable limits. You can simplify. L'Hopital's rule is still too complicated. Come on, it's just Calc 3. We're not like rocket scientists or anything. You can factor this. So you can do that if it's an option. Right, I just want you to know that. We can simplify it. Right? It was hard to do it with that. Like that you can simplify, so you're stuck with using this method. But sometimes if your algebra can help you, you can do it. And L'Hopital's rule in multi-dimension, a multi-dimensional L'Hopital's rule. Well, I guess right now, the suggestion isn't as crazy as it would sound because we actually haven't done limits in the multivariable sense yet. But derivatives are actually complicated, right? Because limits are complicated. Remember, same way in single limits, when you're talking about the derivative was a limit, right? Limit as h approaches 0 of f of x plus h minus f of x over h, right? That was a limit. The derivative behaves how it behaves because the limit only had 2 directions to worry about. What happens to a derivative limit when you have an infinite number of directions to worry about, right? You can't just take the rate of change with respect to x. You take it with respect to y or some other function entirely. The derivative becomes a whole different monster. Just saying, oh, L'Hopital's rule, just differentiate top and bottom. It's not as simple as you would think, right? Derivatives don't work the same way because limits don't work the same way. Okay, so just bear that in mind. L'Hopital's is in Calc 3. It's pretty much never the answer. I want to show you another method, though. Called polar coordinates. Yay! Okay. In polar coordinates, what is x? R cosine theta. You guys took too long. What's y? R sine theta. If I look at the phrase, the term x squared plus, the expression x squared plus y squared, I get r squared. We could actually use this to our advantage. Notice, as xy approaches 0, 0, for example, x squared plus y squared would approach what value? As x or y approach 0, x squared plus y squared would approach 0, right? This would mean r squared would approach 0, which would mean r would approach 0, right? Okay. We're going to use that to our advantage. Let's do one we've done before. X squared y over x squared plus y squared. I'm going to show this limit exists, but in a different way. It turns out that I can actually transform this guy now in polar coordinates. Meaning, I realize that as xy approaches 0, 0, it's the same as saying r approaches 0. Right? And then what I can do is I can replace all x's with r cosine theta, replace all y's with r sine theta, and if I see the expression x squared plus y squared, I can replace it with r squared. Right? So I'm going to go here, this is r squared cosine squared theta, this is r sine theta, and this is r squared. My r squares will cancel. I get the limit as r approaches 0 of r times cosine squared theta sine theta. Now as r approaches 0, what does that give you? Just gives you 0, right? You have 0 times whatever, it's going to be 0. So that's it, the limit is 0. Yeah.
Well, for most of the ones we've done so far, you get 0 over 0, like there is no point at the actual thing. And I know that doesn't matter, top 2 doesn't matter. But if there's a function that we can plug in the points and get an answer, can we say that's the limit?
Yes.
Okay.
So that's also true, as what's true. What I was going to mention that when we talk about continuity, but we won't have time to do that. But yes, if your function is continuous at the point you're taking the limit, just plug in the answers, right? So for example, if I took the limit as I approach 1, 2, then just plug in 1 for all the x's and 2 for all the y's, and whatever that number is. So when it is continuous, we can just plug in the point. Yes. Right. It's when it's not continuous, that's when the crazy things happen. We'll stop there for now. We didn't finish the section, so no homework. Thursday we have the test. Make sure you do those review problems. The test covers chapter 10 only. And I will see you guys on Thursday. I didn't take attendance. I'm using the quizzes.